A few things. As some of you saw from the email, there seemed to be doubt that the 70 solar mass black hole exists. You can find more details of those papers that I sent last night. But overall astronomy is exciting. There are also reports on new views of the sun from close in. So in this wintry weather, if you wanted to see them, they were obtained by the Parker mission. Very beautiful images of eruptions on the sun. And today we have a very special set of talks of the new postdocs that came to the BHI. And I should confess here that you know, one evening I went home and I told my wife, you know, the BHI is really amazing because I get to see some of the most brilliant young people that I've never interacted with just being in the astronomy department. Sorry, Ramesh, but I don't know if you...
Yeah.
No, but...
Young at heart.
But it's really... I mean, I sincerely mean that it's an intellectual treat to interact with some of you. And today we will hear from the 4 new incoming postdocs, but of course the ones that are here already are also as brilliant. Is there anyone that is making the introduction? Okay, Paul.
All right, so
and it's a tight schedule, right? Like
I mean, they're going to be 15 minutes long instead of 30 minutes because we got 4 guys speaking, and you can ask questions as normally. It's nice that we have a fair amount of people here today too in the holiday. So thank you all of you guys for coming and giving the 4 speakers a hard time. So Kevin,
Yep.
We're not going to give him that hard. So Kevin will be our first speaker today.
Yeah. Okay, so hi everyone. In this short talk I will talk about chaotic properties of black holes, and in particular in the ADS-CFT context. And I will mention some of the results that were published in collaboration with Vijay Balasubramanian from UPenn, and with Ben Krabs and Marine de Klerk from Vrije Universiteit Brussels, where I did my PhD. Oh, what is that? Okay. Take this here. So, yeah, oh, sorry. So first of all, a quick reminder of the notion of chaos in classical mechanics, for which this Lorentz attractor is a very famous example. So, classical system will be said chaotic if small deviations in initial conditions lead or may lead to divergences in trajectories at a later time. So in this case, for this attractor, you have some trajectories that just go around in the same wing of the butterfly. But for very close trajectories, you just go over to the second wing of the attractor. So that's an illustration. And the mathematical criterion for a system to be chaotic is that the variation of the position at time t with respect to some initial condition or to initial conditions behaves exponentially with time. And so the exponent here, we call it Lyapunov exponent. So as you notice, you can also rewrite this quantity as the Poisson bracket of conjugate momenta, which gives a hint at how we can generalize this criterion to quantum systems. So now, there is something quite similar happening in the context of black holes, and in particular for particle scattering close to or in the neighborhood of black holes. So here I've depicted an eternal black hole with anti-de Sitter asymptotics. And in that geometry, there is a 2-to-2 scattering close to the event horizon. So what you can notice is that the center of mass energy of this scattering process gets an enhancement factor, an exponential enhancement factor, compared to the energies of the particles, the ingoing and outgoing states in the asymptotic region. So this exponential factor is an exponential in time, where the time is the time difference measured by some observer at asymptotic infinity between ingoing and outgoing states. And so the Lyapunov exponent is identified with the surface gravity of the black hole, or equivalently with the Hawking temperature.
Wait, sorry, so this is the energy in the center of mass?
Yep.
Right, and the intuition is that if delta t is very large, they had to collide very close to the horizon.
So the intuition is that if delta t is very large, they are accelerating. They are accelerated during longer time before colliding, before interacting. So yeah, that's actually the intuition. It's nothing very fancy, but it tells you that small perturbations in the asymptotic region may result in high energy scattering or violent physics close to the horizon. So that's, if you think about that, it's again some kind of chaotic behavior. So
excuse me, if
yeah.
you imagine that there is like a perturbative scattering between the particles, how the perturbation would shows up here?
If I imagine that?
I mean, because this is like a 2x2 scattering, right?
Right.
So there are some like a perturbation actually associated with the scattering itself.
Yeah. So I mean,
does
everything is encoded in this blob. So you have like,
Okay.
I mean, this is like these are the in and out states, and everything perturbative is in the blob. So you have graviton exchange, loops, everything.
Yeah. So if you imagine to go to very low actually values of a scattering, could it be that you have some controls on the chaotic behavior, or there are two different things? You see what I mean?
Yeah. No, I'm not sure.
Okay, we can talk
Okay,
later.
yeah.
Yeah.
Okay. Thanks.
Another question. You talk about ADS black hole, but
Yeah.
even not without ADS,
Right.
when particles get close to the horizon, they could gain a lot of energy.
Sure.
And,
Yes.
and so in normal black holes, you could also have situations.
Yeah, right. So I mean, this is more generic than just ADS black holes.
Right.
But so in what follows, I will make sharper this analogy with chaos in the ADS CFT context. So that, I mean, that's why I have this picture. But you're right. Okay. So
And in the classical case, the trajectory or the position was chaotic, but here is the energy. Can you also make a similar statement with the trajectory as well here?
yeah, I'm gonna do that. But
Okay.
for that, I need to go to the ADS CFT correspondence. So as you probably know, the ADS CFT correspondence is a duality between gravitational theories of space-times with ADS asymptotics and quantum conformal field theories in one-less dimension that are strongly coupled. So you can think of the CFT as living on the conformal boundary of the ADS space-time. That's a rough picture. And in that context, static black holes have been shown to be dual to thermal state in the CFT at the Hawking temperature. Gravitational collapse corresponds to the process of thermalization. The quasi-normal ring down of black holes that is depicted here, so you have like some perturbation on top of a black hole, it gets swallowed, the black hole has some ring down and returns to its equilibrium configuration. This is dual to dissipation in the CFT. And what I want to talk about now is that particle scattering in ADS encodes chaotic properties of the CFT. So, okay, what I'm going to do is I'm going to ask whether the CFT is chaotic. And what I will show is that to answer that question in the ADS-CFT correspondence, I basically have to compute the kind of 2-to-2 scattering that I was mentioning. Okay, so we had this criterion for chaos in a classical system. So now we want the similar criterion, but for a quantum system, and that has been proposed by Larkin and Ovchinnikov in '69. So you just replace the Poisson bracket by a commutator, the conjugate pair of momenta Q and P by any pair of Hermitian operators. And because now it's a quantum system, you have to take expectation values in some state. And because you don't want to average out the exponential increase, you take the square of the commutator instead. So that's the criterion. And you can also think about this commutator square as telling you how much of the information initially contained in the V perturbation, so the V operator, how much of this information is scrambled into the other degree of freedom W at a later time t. So, and in particular, when this is close to 1, in this quantity, we say that there are significant scrambling of the initial perturbation into the degree of freedom W. Okay, so what we have proposed in our recent work is a new approach to compute this kind of commutator square. In the ADS-CFT correspondence, that's an important point. So, and it works in any asymptotically ADS space-time. There is no requirement on symmetries, so it extends like earlier methods. And so this approach is based on a WKB approximation to field propagation in black hole geometries, in which basically you can just study the field propagation by studying geodesics in that space-time. And what we found is that the main contribution from this kind of commutator square comes from the graviton exchange of pairs of free falling particles. So it's essentially the kind of scattering process I was mentioning at the beginning. So
I think that was actually my question. So you know that you are actually supposing some effective field theory approach to model the exchange of gravitons in like a scattering.
Yeah.
So I was wondering whether the coupling constant that you put for this actually would affect your chaotic behavior somehow, or?
Yeah. So here it's in the ADS-CFT context, and we're looking at like so you have a specific gravitational theory and basically I mean, here we look at the truncation, which is GR essentially. So it's just GR, and the coupling constants are fixed. So yeah, so let me illustrate a bit more in detail how this works. So first of all, you have to pick geometry, which corresponds to picking a state, a quantum state in the CFT. So here we've looked at the so-called Vaidia geometry. It's a time-dependent state where you start with a black hole, but you also create a thin shell of dust from the asymptotic region. This shell of dust collapses and is swallowed by the black hole, which increases its mass. And so on the CFT side, this is due to a thermal state where you inject some energy at some moment of time, and therefore it heats up to some higher temperature state, higher thermal state. So now we want to compute this commutator square of two operators V and W, which are inserted on the conformal boundary of the spacetime. So remember that that's where the CFT can be thought of leading. So now our method shows that to compute this in the WKB approximation, you just have to find geodesics that connect those boundary insertion points and compute the so-called iconal phase associated to the scattering of these geodesics. So, okay, let me tell you how you can do that. So you take the particle V that goes on the red geodesic. You compute the gravitational field it produces. It's called a gravitational shockwave. Okay. And you contract it with the stress tensor of the other particle. And then you do the reverse and you have this expression. Okay, so some quantitative result. This was the static black hole case. It was studied by Shankar and Stanford from the gravity picture, by Roberts and Stanford from the CFT picture. They found agreement. And this is the result. So this is the iconal phase, or the commutator square, essentially. So, and we recover this exponential increase with pi. Okay, so this shows that the CFT at thermal state is chaotic. And this Lyapunov exponent is identified with the Hawking temperature, as I was saying. So in addition to that, there is also some spatial dependence, because you can separate the operators spatially as well. And what we are interested in is this red line. So these are the level sets of this function. So there is this red line, which is where the commutator square has value 1. So this is when and where scrambling has been efficiently achieved. And we associate velocity to that line called butterfly velocity. So the butterfly velocity tells you how fast the region where information has been efficiently scrambled grows. So in this case, it's just a light velocity. So now let me finish with what we have done. We've looked at this Vaidya geometry. These are the level sets. So this black horizontal line is the moment of energy injection into the system, or from the gravity picture, it's the time at which a thin shell of dust is injected from the asymptotics. So below that horizontal line, the level sets are the same. But after that, you see some modification. And in particular, what is interesting is that the butterfly velocity associated to the red line now becomes superluminal. So actually, right after energy injection, it's given by the ratio of temperatures after and before energy injection, and it's greater than 1. So this is this is a qualitatively new result, in the sense that it's the first time, as far as I know, that people find a superluminal butterfly velocity. But I should tell you that this doesn't mean that there is causality violation. Causality violation would require to have some non-zero value of the commutator squared outside of the light cone, which is not the case. So here, outside of the light cone, it's just 0.
Why does the plot end on the right?
Right. So here we haven't been able yet to find an expression, but we are working on it.
So what's the meaning of a superluminal velocity? It's not carrying any information.
Right. So it's not like there is a local degree of freedom propagating along this line. It's just the size of a macroscopic region. So the boundaries of that region are not carrying any information.
So it's like a phase velocity.
Yeah. Yes. Somehow. Yeah. Okay. Well, that's all I wanted to say.
question for Kevin?
So this superluminal butterfly velocity, this is in ADS.
Yes.
So what is the equivalent signature in the CFT?
No, so this in fact is a CFT quantity.
This is the CFT quantity. Okay.
Yeah, yeah.
So in the gravity, it's just Vaidya.
Yeah, the gravity is Vaidya with some scattering process. Yeah.
Okay.
But this is what you need to compute
Compute this.
the chaotic properties of the CFT.
So what is the, I know this is a naive question, but what is the observational signature of that? I mean, because like what you guys said, this is a phase velocity, right? So.
Yeah, right.
But is this anything that is physically occurring that is different than,
So it tells, I mean, what it tells is that you have some initial perturbation to the state. This initial the information of this perturbation is scrambled into the other degrees of freedom, will travel along the system. And this butterfly velocity is a measure of how fast significant amount of scrambling spreads into the system. Yeah.
How does this scale with the energy that you inject? Because naively you would think if you inject more energy, then you can make the velocity increase. Is that the case?
You mean here? This?
Yeah.
Yeah, so this, indeed, so if you increase the energy here, that means that you increase the late time temperature. Yeah.
All right, let's thank Kevin.
I mean, these are related quantities.
How do we change screen?
So you know what? Oh, you got to plug it in. Yeah. Good. And then we go to.
No.
Right, it's just
It's not. So it's it's not
Prepared system.
Okay, everybody. So our next speaker is Max, and he's going to tell us about geometry from counting problems. Go ahead.
Thanks. Okay, I'm going to tell you about geometry from counting problems. So the star of today's talk is K3, which is a four-dimensional manifold. So here is pictured K2, and then if you add a K, then you get K3.
Sorry, what is K?
It's, well, depending on who you ask, it stands for Kamar, Kadira, and maybe Kaler. Okay, so the main thrust of this talk is a new physically motivated approach to determining the simplest non-trivial Causality geometry. So I'm gonna, because the string theory plays an important role in our procedure, I'm gonna introduce string theory. I'm also gonna introduce string theory because the reason we care about Causality manifolds is largely because of string theory. There's a tension at the heart of modern physics. On the one hand, as we all know, general relativity works very well at large length scales, describing massive objects. On the other hand, we have quantum mechanics, which is fantastically successful at the subatomic scale and atomic scale. Reconciling these is very difficult because general relativity is non-normalizable, and so it needs to be UV completed to some UV complete theory. And that's what string theory is. This incompatibility, as general relativity and quantum mechanics are generally very useful, but there are regimes in which both effects are very large, and so you do need to have a theory of quantum gravity that reconciles the two effects. And so the paradigmatic examples of these are black holes and the early universe, where you have very large energies involved, but you also have very short distances involved. And so, okay, so a star of this talk is going to be a notion called supersymmetry. So as we all know, when J.J. Thomson discovered the electron, J.J. Thomsino discovered a particle with the same mass but opposite statistics called the selectron. So this is a very important symmetry in nature.
Which way? Why do you say in nature? We haven't found it yet.
No, Thomsino found the selectron. Okay, good.
On your slide.
Yeah.
But not in reality.
Okay, as it's been pointed out, I'm lying.
But it's okay.
And supersymmetry is in fact of questionable experimental value, although I think a lot of us still hope that it is phenomenologically relevant, but that will not be the reason that we care about it in this talk.
I asked this to everyone. Can you conceive of string theory without supersymmetry? I mean, are tachyons the one thing that you want to avoid by introducing this supersymmetry, and can you work with it without supersymmetry at all?
So critical time-independent, like perfectly stable string compactifications seem to require 10 dimensions and either 16 or 32 supercharges, but that's a very special situation. Yeah, generally there's no particular reason that a string compactification needs to have any amount of supersymmetry. It might be hard to describe, or it might be time dependent, but yeah, there are plenty of tachyon-free, totally non-supersymmetric string compactifications.
I guess it depends on who you ask, because I asked Jim Gates and he was like, oh, why even ask the question? You need supersymmetry for any consistency. But anyway,
well, so again, it depends on what adjectives you're adding before string compactification. If you really do want like time-independent, stable, critical, perturbative string theory, then I think that's enough adjectives to require you to have the usual 5 perturbative string theories.
Okay.
But that's a lot of adjectives to add.
Thanks.
And in particular, our universe is time-dependent, and non-supersymmetric. So there are very good motivations for caring about non-supersymmetric compactifications. Okay, so in our talk, there are 2 reasons that supersymmetry plays a role. One is that it gives a useful toy model for studying a lot of phenomena about, for example, black holes. So questions that you have about actual black holes, you can answer them by studying very supersymmetric black holes, and you can learn a lot of lessons about that are generic to any black hole by studying these. So maybe the paradigmatic example is Strominger and Vafa's count of black hole microstates using very supersymmetric string compactifications, but their results are expected to be far more general. And then the other reason that we care about string supersymmetry is, as was just alluded, the main 10-dimensional perturbative string compactifications are all required to have various amounts of supersymmetry. So I've pictured the 5 perturbative string theories that all live in 10 dimensions, as well as M theory, which is basically 11-dimensional supergravity, but it's got a UV completion to some theory that's a quantum theory of gravity. It's not a string theory, but it's still related via, it's part of this web.
What's the thinking now that there are all these possible theories, all of them are viable? Are we incorporating all of them as in our thinking, or are we saying that one of them must be right and the rest are not?
This is an excellent question, which brings me to this picture. So raise your hand if you think this is a rabbit. All right, raise your hand if you think this is a duck.
Wow.
Okay, so I need to pick a better picture. the point of this picture is to illustrate that depending on how you look at something, you can describe it in different ways. This is a very common phenomenon in physics, where called duality, where the same physical system can be described using a totally different language, and both languages might be useful for illuminating various aspects of the physics. So if you go back to the duality web, it's conjectured that they're all related by these dualities, and so they're all really part of the same physical theory, and they're just in various limits. One version of the theory might be useful, for example, for describing perturbation theory, but they're all equally, they're all the same theory. It's just various ways of describing various things.
And that was proven mathematically or not?
None of this is mathematically rigorous, but there's significant mathematically rigorous evidence supporting these duality conjectures. There are certain conjectures that are literally rigorous, but that's generally rare. Most of the most interesting conjectures are conjectural. Or dualities are conjectural. Conjectures are always conjectural. Okay, so I've used the word compactification a few times, so let me now say what that is. We live in 4 dimensions, but as I've just alluded to, string theory naturally lives in higher dimensions, generally 10 or 11. And so in order to reconcile those two facts, we generally imagine having higher dimensional spacetime, but most of it is compact and has a very short length scale, characteristic length scale, it's called the Kaluza-Klein scale, such that that there's an effective description of physics that is 4-dimensional that applies as long as you're at energies small enough so that you can't resolve the extra dimensions. So just an example for how that might work. If you have just a 5-dimensional spacetime where the 5th dimension is curled up into a circle, and you have some field that resides in 5 dimensions, you can Fourier expand it out to where the Fourier coefficients are some 4-dimensional field times the e to the I. Okay, yeah, the Fourier mode. And if you just plug that into the action, then from the 4-dimension, integrating over the 5th dimension, you get an effective 4-dimensional theory with an infinite tower of Kaluza-Klein fields whose masses are of order the characteristic mass scale set by the characteristic size of the compact manifold. And so you see here that the geometry of the curled up dimensions plays an important role in determining what the physics is, what the 4-dimensional physics is. And so this is the main motivation for understanding all of these geometric questions in string theory, that the geometry of the compact manifold plays an essential role in determining what physics what physics.
This one looks like a mass, right?
Exactly. So in that case, it was a mass. And in general, yeah, your fields will have masses of order the Kaluza-Klein scale, but then there will be other interactions as well. Okay, so a sort of cartoon of what I've just outlined in compactification is if you have some solution of the vacuum Einstein equation, so some Ricci-flat 6-dimensional manifold, you plug that into 10-dimensional gravity, and it'll spit out via the Kaluza-Klein reduction some theory of 4-dimensional physics. And again, the reason that one might care particularly about 10 dimensions is because that's where string theory happens to be happiest. And now just adding in some extra symmetry, supersymmetry, let me specialize to a very special type of Ricci-flat 6-dimensional manifold called a Calabi-Yau threefold. And the 3 is because they naturally have complex coordinates on them, and so we count using complex dimensions instead of real. So Calabi-Yau threefolds are in particular Ricci-flat 6-dimensional manifolds, but they have some extra structure. Similarly, rather than having just 10-dimensional gravity, I'll have a supersymmetric version of 10-dimensional gravity. And if I combine those ingredients, then again via Kaluza-Klein reduction, I get some 4-dimensional physics with some amount of preserved supersymmetry. Yeah. Oh, sorry, that was 5 minutes. So yeah, so Calabi-Yau manifolds are of interest to physicists because they give you supersymmetric string compactifications. Calabi conjectured that these metrics exist, and Yau famously proved that they exist. But the proof is a very creative existence theorem, but it's not constructive in the sense that it doesn't actually tell you what these metrics look like. And indeed, to date, we know of no, we don't know any examples of compact Calabi-Yau metrics besides tori. And so until very recently, the state of the art was very dismal. It was, I think, widely expected that such metrics couldn't be written in closed form. So, yeah, the main result of our recent work is that we have a procedure for reducing the determination of Calabi-Yau metrics, in, at least in the simplest case of K3, although it generalizes in very many axes to other manifolds, to a problem that we haven't solved yet, but it's a morally solvable problem that we're working on solving. And this is what I alluded to as the counting problem in my talk. So just some examples of what a Calabi-Yau manifold is. In 2 real dimensions, the only example is a torus. In 4 dimensions, you have a 4-dimensional torus and then K3. So this is sort of one reason that K3 plays such an important role is it's just the simplest non-trivial Calabi-Yau manifold in this sense. Okay, so the last bit of string theory I need to introduce is just what is a brane. It's just some p plus 1-dimensional thing that lives in string theory. Yeah?
You said K3 wasn't a 6-dimensional.
Sorry? Oh, yeah, K3 times T2 is what you would use if you wanted to get a simple 4-dimensional compactification. Okay, so what I'm going to very quickly sketch for you now is the results from this paper that I wrote with my advisor Shamik Katru and Arnav Tripathi, where we explained how to get K3 metrics from a physical system that resides in string theory called a little string theory. So the idea is if I have some physical theory with a very complicated effective potential that looks like this, at low energies, most of this complicated potential is totally unimportant because I'm going to be stuck near the bottom of the potential. And so for as long as I'm at low enough energies, all I care about is the geometry of the bottom of the potential.
By the way, the axiom is this.
Yeah, exactly. So I just my low energy physics is characterized by what's called a nonlinear sigma model, which is just a theory describing the dynamics of this particle exploring the bottom of the potential. And the bottom of the potential is called the moduli space. And there's a natural way in string theory to construct physical theories whose moduli spaces are some Calabi-Yau manifold that you care about. Namely, just consider sticking some object transverse to the manifold you care about, and use it as a probe of the manifold itself. So now the moduli space of this orange probe is the say K3 surface itself.
Is it a chopstick?
Well, in the case we have what's called an M2 brane, which is 3-dimensional. So it's a 3-dimensional chopstick, I guess. But I'm not good at drawing 3-dimensional things, probing 4-dimensional things. So we're stuck with that. Okay, so then via what's called heterotic M-theory duality, one of the dualities I alluded to earlier, M-theory on K3 is dual to just heterotic string theory on a torus. And we understand tori very well, so this is a much easier problem for us to work with. And similarly, we can make the theory purely perturbative, meaning have the heterotic string coupling be small, just by taking the volume of the K3 surface to be small. And then the M2 brane becomes dual to something called a small instanton 5 brane. And the theory that describes the dynamics of this 5 brane is what's called a little string theory. And the sort of amazing thing about little string theories is despite the fact that the string coupling of the big string theory is vanishing, the coupling constant of the 5 brane is still non-zero. They're just very strongly interacting objects even at weak string coupling. Okay, so then I want to just compare this with another duality called mirror symmetry. This is a duality in string theory that relates one type of string theory on one Calabi-Yau manifold to a different string theory on a different Calabi-Yau manifold. And Strominger, Yau, and Daslow explained that, that mirror symmetry should at least morally relate the determination of a metric on one of these mirror pairs to a certain counting problem on the mirror pair, on the other Causality manifold, where you're counting certain special submanifolds that sort of look like this living inside of the mirror pair. But it was never really explicit how one could possibly do this, and certainly no one ever thought one could use this to write down a formula for what the metric was that summed up all of the effects of these submanifolds. But using the extra structure given to us by the little string theory, we were able to make use of this philosophy, but actually write down what the formula is. So at this point, the state of the art is if we have the solution of this counting problem, then we can just plug it into the formulas from the little string theory, and we'll have the metric. And then one other, the theme of this talk is using string dualities to make things easier. So let me just mention one other duality, where now there's just another way of formulating this little string theory using a totally unrelated auxiliary Causality threefold, this is called geometric engineering, and you can, and I use this picture of a cone because the threefold is now singular, and you can now relate the counting problem we care about to a certain counting problem, again, involving this geometry. So, okay, hopefully I've conveyed the spirit of our work. Yeah, thanks.
Okay, one quick question. Anybody? Can you, oh, sorry, I thought you were asking. Can you construct these Causality geometries numerically?
Yeah.
Okay, good. All right, let's move on to our next speaker. So it's just doing it analytically, this stuff.
Yeah.
It's just elliptic PDEs, right? Because they're Riemann. It's just elliptic
This is probably great. Like, yeah, very fancy. It's actually got more structure than Einstein equations, so it's in a sense easier.
It's not turned on.
What do you say when you mean morally? You mean you say morally. There's a lot of mathematicians say morally.
Oh.
I'm not sure what that means. It means not exactly. But
Yeah. Spiritually,
in good taste.
Yeah.
In the same manner.
All right, so next we have Achilleas telling the connection problem for ADS2.
All right. Okay, so what's the connection problem for ADS50? Before I explain what that is, let me just remind three basic facts. The first fact is the near horizon geometry of black holes which are near extremality is always ADS-like. That's actually a theorem proven by this gentleman here, basically. It applies to very wide class theories, wide class of theories of gravity. And it basically is a statement about degenerate horizons. In particular, it applies to the astrophysically interesting case of four-dimensional extreme and near-extreme black holes in pure Einstein gravity. And the near horizon of extreme care, NEC for short, is written in this line. So you can see that it is ADS-like because it has this TR part there, which is ADS2. There is a vibration over it here, and the warping by this factor over there. So with the warping and the vibration at a fixed polar angle, it's also called warped ADS3, or it can even be locally exactly ADS3 if that warping factor is 1. But this is the sense in which it's always ADS-like. It's true even in four-dimensional extreme care. Now the other fact that is by now apparent is that 20 years after the discovery of ADS50, we have really a paradigm shift in a lot of modern theoretical physics, and that means. But what I mean by that is that there is a class of more general gauge gravity dualities. So things like ADS QCD. So there are these dualities between gravities in asymptotical ADS spacetimes and quantum chromodynamics, beyond standard model physics, condensed matter theory, and even atomic physics like cold atoms and stuff like that. So the question I want to ask though is why isn't Astro CFT also a big enough thing?
What do you mean by that?
I mean, this acronym Astro CFT is something that I wrote down. The others exist in the literature. You can look them up. So if you search for any of the top things on the archive, you will find hundreds of papers. You will not if you search for Astro CFT. So what is the reason for that? You could come up with various answers. Some of them are sociological.
Before answering, what do you mean by that? What do you mean by Astro CFT?
Oh, I mean a duality between astrophysics and a gauge theory that would be like a CFT. So none of the gauge theories on the right-hand side of the dualities in the first line is exactly a conformal field theory.
But when you say astro, you mean a black hole that is astrophysical, or what do you mean by astro?
I would be happy with with anything that that would mean that we're describing astrophysics in terms of.
I mean a planet, a star.
Anything. I mean, anything that any corner of astrophysics that we could use ideas from gauge gravity dualities to do computation, or going in the other direction, informing gauge theories from.
But there is one really concrete example, though, right, of just studying near extremal black holes, right, where you can use Kerr CFT.
Yeah.
That's what I was thinking, but he says astro in general. I don't understand.
Yeah, well, this wasn't a very deep statement. I mean, Kerr CFT is does belong there, but the question is why isn't it big? I'm not saying that there doesn't exist anything. There does, and this is what I and many other people in this room have been involved in. But it's not as as big as any of the other things. And what was the main hurdle in, or what I think is one of the reasons for that is that people thought that, okay, in the real world, gravity does not obey anti-de Sitter boundary conditions. So if you go to an astronomer and you ask him, why aren't you thinking about ADS-50? Well, the first thing they might say to you is that I'm an astronomer, I do gravity in asymptotically flat spacetime.
No DS.
Or I'm an astronomer, I do cosmology, so I use the Sitter boundary conditions. Exactly. So one of the two, but not anti-de Sitter. So that is one of the reasons. Yeah.
In the Astro CFT, I guess very loose duality, would you consider the interior of neutron star part of the CFT? I mean, it's like a quantum liquid in some ways, or part of the Astro or both.
Yeah, I mean. As I said, Astro CFT is not a thing, it's something I came up with for this slide. So I would be willing, yes, to there are papers actually which are doing this kind of thing. But they are more, I would classify them more here and here. So they're basically trying to deduce what the equation of state for neutron stars is. So they're doing QCD using gravity. Okay. So question is about boundary conditions, mainly. You have to go beyond anti-de Sitter boundary conditions, and therefore you have to solve this thing I call the connection problem. So what do I mean by that? I mean, you have to take solutions to anti-de Sitter and extend them away from the near horizon to connect them with solutions in gravity with asymptotically flat regions. Or de Sitter for that matter, but in this talk I will be thinking about flat. Okay, so there are some things which are known. So what solutions exist for this connection problem? Well, actually, there is a solution for the connection problem of scalar, vector, and gravitational perturbations of this neck geometry that I showed previously. It was found by this gentleman in the 70s who were studying superradiance for Kerr black holes. They didn't know about the neck metric, which was discovered more than 20 years later. But if you think carefully, they have solved the connection problem for perturbations of neck because they have been able to find solutions of the Kerr perturbation problem and identify the part of them which is the solution to the neck problem. And we have also recently solved the same problem for geodesics, so for null geodesics, which will originate in this neck geometry, and then extend all the way to flat infinity in Kerr.
Excuse me, sorry, 1 second. Could you go back to the previous slide? Just explain what the connection is. Are you trying to glue two things together?
I'm trying to solve the anti-de Sitter equations, so perturbation equations or null geodesic equations, and anything that I'm doing in ADS, and then also have that realized as a solution of a problem which includes an asymptotically flat region. All right, so this having that connection problem solved is paramount if you're trying to make any connection with astrophysics. And so the first thing was very useful for us, for all of these people and many more, to do computations of extreme mass ratio in spiral gravitational wave signals for a situation where the center of black hole is nearly extremal. And this is directly relevant for LISA. Having the null geodesic solved is very important for doing things like imaging hotspots or doing line reverberation calculations. So there's here some lists of people. Hopefully we can find some friends in that list. It's non-exhaustive, but I hope you can find some friends in that list and ask them more about that. This is not what I'm going to talk about. The last thing I want to say is, as far as motivation is concerned, is that the holographic arena for all of these studies was the scarce CFT correspondence. But I think it's fair to say that we don't understand the dual field theory, dual to neck, well enough. And the reasons for that, in one way or another, all have to do with this complicated vibration over ADS2 that varies with the polar angle that I mentioned at the beginning. So in this talk, I'm going to focus on an example with more symmetry. So just take a direct product of ADS2 with the two-sphere. So this is not as relevant for astrophysics, but I say it's only phenomenologically removed from astrophysics. It's still an exact solution of 4D Einstein gravity coupled to electromagnetism, and it's the near horizon of extreme Reisner-Nordstrom. Also, it's increasingly well understood in recent studies of so-called SYK and related quantum mechanical models. So this talk will be about solving the connection problem for perturbations, gravitational and electromagnetic perturbations of ADS2 cross S2 in 4D pure Einstein-Maxwell theory. Okay. All right. So a quick reminder, a quick review of ADS2. So there's something called ADS2 and something called near ADS2. So if you have a black hole which has charge Q and mass m, you can measure the deviation from extremality by this parameter kappa. So kappa is equal to 0 is the extreme Reisner-Nordstrom, small kappa is the near extreme one. And if you use a dimensions radial coordinate such that the horizon of the black hole is at r is equal to 0, then the near horizon of extreme Reisner-Nordstrom is exactly ADS2 cross S2 in these so-called Poincare coordinates. So we've got the ADS2 here times the two-sphere. If you have a nearly extreme black hole, so kappa is small but not 0, and then you look at a region where r is of order kappa, so still very near the horizon, then you get this solution, and this is what I call near ADS2. There's also a gauge field here, so these are actually the Bertotti-Robinson universe, which was discovered independently much earlier. The one important thing to say about these things is that the two are actually locally diffeomorphic, so there's a coordinate transformation that will map one to the other, and that reflects in these Penrose diagrams. So the global version of either of the two is just a strip, like ADS2, with two disconnected time-like boundaries, and the first one, the Poincare patch, reaches all the way from one boundary to the other, whereas a smaller one like this is the near neck. So if you are doing, so this is ADS, so there's no asymptotically flat region here, and there's a time-like boundary. If you do, as I will, attach the asymptotically flat part back, if you attach it here, you will get near extremal physics, near extremal Reisner-Nordstrom physics. If you attach it over there, you will get extremal physics. How much time do I have? 5 minutes. Okay, so this is what I mean. So the Penrose diagram for the extremal black hole is this. So here's future null infinity here. So this little triangle here is the near horizon in the previous picture, whereas if you have the nearly extreme horizon Nordstrom, the outside of the black hole with the null infinity there is this, and this is the near ADS2 part. Okay, so it is in this context that I want to solve the perturbation problem for coupled gravitational and electromagnetic perturbations of ADS2 cross S2, also extending whatever solutions I will find here all the way to the asymptotically flat part. Okay, and this is summarized, the steps to do all of this is summarized in this slide. So the rest of the talk will be technical, include many formulas, but this is really the take-home message. So how you're supposed to do this? Well, first you write down the linearized Einstein-Maxwell equations and you reduce them on the background of the black holes to a single fourth order radial ordinary differential equation. Why fourth order? Because we have 2 gravitational and 2 electromagnetic degrees of freedom, so we should be expecting a fourth order equation. Then you look at this equation, you find the appropriate near horizon approximation, which will identify a solution that corresponds to the ADS problem, to the problem of solving this same perturbation question in ADS2 cross S2, and solve that problem as well. Then you find 2 other solutions in so-called intermediate and far region approximations in such a way that the 3 of them together cover the entire space-time. And then you also want, of course, the additional 2 equations to also be solvable. If you succeed in those steps, then in the final step you use what's called the mass asymptotic expansions method, glue the 3 solutions together, and have your connection problem solved. And the thing that I want to emphasize is that all of this has been done entirely analytically. There is no numerics involved in any of these steps. So this is a good place to ask any questions because the rest will be the flat of formulas. Okay.
Sure. After you do this, what does this now tell you about ADS CFT?
Sorry?
What does this now tell you about ADS CFT or flat CFT after you finish doing this?
What does it tell me about ADS CFT?
Well,
this sets up the stage for actually taking anything you know about ADS CFT and ask what does it tell you about asymptotically flat physics.
So how would you actually do a computation? Do you start in ADS, go over to this?
Right. I'll try to go over how I do the calculation in 3 minutes, and you'll see.
But I don't see any actual gauge gravity duality here. This is all just on the gravity.
That's right. Yeah. So this is a purely gravitational computation. If you want to do a gauge gravity duality for asymptotically flat, you take whatever you know on the gauge side of ADS2, and you try to see what you learn from the matching on the gravity side that I will describe here, and see whether there is something you learn about flat physics. Yeah.
I see. So you're
saying
this
is the first step in a long road of extending.
This is how you would derive quote unquote flat CFT, but I mean whatever. That's way overblown.
This is how the stage has to be set to do an extension.
But it's not obviously mathematically correct, right? I mean, you can glue things in one side and it may not glue on the other side.
That's right. You will need to understand. There's a lot to understand as to So here I will understand basically how the diffeomorphisms of ADS2 are broken and how the thing then.
Just to be clear though, you're allowing the boundary geometry of ADS to be time dependent, right? That depends on
I don't even really have a boundary. I'm allowing stuff to flow in and out of the boundary because I want to have.
So in that sense, this is all mathematically consistent.
Yeah, the gravity computation here is all mathematically consistent.
But what the dual also satisfying that?
I don't.
It better does, but I don't have a. I'm not saying something about.
I mean, but it would be conjecture.
It would be informed by this computation. It will have to be analogous. The duality will have.
It wouldn't be a crazy conjecture to make. I don't think so at all.
I'm not even making any conjecture at the moment. I'm just doing this gravity computation, which should inform whatever you want to do about the conjecture you will make. All right, so let's go over this very quickly. Step 1. This is the most general answers for solving the Einstein-Maxwell equations, even parity sector, because of spherical symmetry and time translation symmetry. You can expand like this. You reduce the Einstein equations to this fourth order differential equation, only on this size of the two-sphere, the perturbation to the size of the two-sphere. and you will have to solve this equation. Now this is a fourth order equation. The other components are all algebraically determined in terms of k and its derivative when you do this reduction. I redefine k to h because that's useful and needed. And the one important thing to note is that if you want to have a solution of the ADS2 problem, then you need to consider modes which are low energy. So this is the other important thing to keep in mind. So once you do that, then you can find these three approximations that I talked about: a near approximation to the equation, an intermediate static approximation, and a far approximation. So this near one will be the ADS one, and these other two will be different ones. So fortunately, they are solved. This is the solution in the static region. It's static because it doesn't depend on omega, as you can see. And even this far one is kind of complicated given in terms of the spherical Hankel functions, but fortunately it exists and can be solved. So this is the most general solution. There are 4 arbitrary amplitudes to your gravitational and electromagnetic waves. These are the 2 near solutions. The near solutions differ whether you're in exactly extreme Rising-Nordstrom or near extreme Rising-Nordstrom, because this is the solution to ADS2 and this is the solution to near ADS2. But they exist, and they're also analytically given by these functions. You have the 4 arbitrary amplitudes of the near solution here. So what is a solution to the connection problem is to relate, say, the near amplitudes to the far amplitudes, or the other way around. So you want to know how you take this near solution, arbitrary boundary conditions, arbitrary 4 constants, and how you determine what it corresponds to in terms of the far solution that LIGO would see here. So this is what we want to do, and the way to do that is to use this method of matched asymptotic expansions. Because the 3 regions overlap like this, you can match 2 solutions pairwise in these overlapping regions, where the matching solutions are extremely simple, and you can eliminate, say, those static coefficients and find a relationship between the far and the near amplitudes. So that would be a solution to the connection problem. You have an expression that relates the CFs to the CNs. So this just proves the point that the solution exists. Here it is. Just flashing this so that you can see that there is an actual rather elementary formula. And this is the case for the extremal black hole. This is the case for the near extremal black hole. There are some kappas here floating around. And this is the end of the story. Now I have some final comments for the experts, but in the interest of time, I'm going to skip that. Thank you.
Right, we have time for one question.
Yeah. So I have a pretty generic question. So I think that we talked about the example of a neutron star early on, where one could view it in some cases as the as a gauge theory that has a gravity dual, and then maybe in other circumstances as a gravity theory that has a gauge dual. Are there instances where the duals themselves are viewed as duals that we know of? So are those duals? So if viewed as a gauge theory, there's a gravity dual. Viewed as a gravity theory, there's a gauge dual. Now, do we know of instances where there should be a definite relationship between the duals themselves? As in, does that imply that there's some sort of duality among?
There are better and less better known examples of dual gravitational and gauge theories. So sort of the original one, that started ADS50 is the best known example. And there you know basically perfectly both the gravity theory and the gauge theory. And the statement that they are dual means that they're actually the same theory, they're equal to each other. So you're not supposed to be looking for 2 more theories and try to dualize it in that direction. They are dual amongst themselves, and that's a closed thing.
Oh, okay, I was just saying, okay.
Could you just go back one slide so I could look at that while you're discussing maybe? Thank you.
Oh, this? Okay, sure. Yeah.
Do you hear the question too?
When you did geodesics, there's only 1 matching. Why are there 2 matchings here?
Yeah, that's a good question. So there is, right, so as you know, I think, matched asymptotic expansion is an art. So there's no prescription for how it will work. But roughly speaking, if you were to solve any equation via matched asymptotic expansions, you would, suppose you were powerful and you were to solve it numerically, then you would look at your solution and you would see how it behaves. And the solutions I presented here, they behave in three different ways. Basically, there are these near solutions which are wave-like. They are wave-like in the near region, and the other two regions are different. So the solution is wave-like near the horizon. Then it's kind of static. There's just this polynomial behavior, and then it becomes wave-like again at infinity as it should. So you would see that this kind of solution has to behave like that. So it's reasonable to be able to break it in these two pieces. But this is really not to say that in principle there couldn't be some special function that we understood well enough that would say include these two in one formula. That's possible. It's just that I didn't find it. I think this is part of what the art is. You might break it in as many pieces as you need for you to actually be able to write it analytically. But there isn't an answer to why it's 3 regions versus 5 or 2.
All right, so let's thank Achilleas again. And last but not least, we have Martin, who will actually pick up the blackboard. So I guess we have to...
Sorry about making everyone
That's
move.
true on both sides of the barrier. That's true.
I also have to move the camera.
For the geodesics in these spacetimes, you only need to do one measure. It's over there. There is no theory of asymptotic expansion. It's like
turning the light on.
What? Yeah.
Thank you.
It's so hard. But there's just like nobody knows what it works. There are no theorems that show that it works. You got it. Their papers, like they're like deep math.
Am I ready to go?
Yeah.
Okay. Thanks everyone. Thanks for coming. Last talk, so I'll try and not be too long before you get to some cake and everything. I wanted to talk about 2 things. This is all joint work with Agil, Ali, and Professor Yao. It was done in the last 3.5 months, but this is a problem I've been thinking about for a number of years. The rough and basic statement is to say that the Penrose Inequality is a problem that's been open since 1972. We have some new results. We prove it in some new cases. So I'll present very briefly and without any technical detail what we do. We don't fully solve the conjecture because, in short, we have to assume some technical things. But I'm not going to go into that detail. The Hoop Conjecture is a conjecture that Thorne, I think, loosely made in the 70s. So the second punchline of this talk is we have some new results. So we're kind of the first time the Hoop Conjecture has been proven outside of symmetry, but modulo, again, technical assumptions, so it's not, say, the full Hoop Conjecture, neither is it the full Penrose Inequality, but at least it's the most kind of up-to-date things that you can do with current methods. So, seeing as this is an interdisciplinary place, I wanted to describe very briefly the heuristic behind the Penrose Inequality, because I've sat in this room and listened to a lot of math talks, and the Penrose Inequality is a subject that keeps coming back again and again and again, and I don't think anyone really has explained in any of these talks that I've been like, why do we think it's true? So I want to just describe the beauty of this argument, and hopefully it should take me less than 6 minutes, maybe something around 6 minutes, 5 minutes, I hope. And I really want to show you why it's so beautiful and why it's such a nice idea. So the basic point is that the heuristic picture of collapse, the heuristic picture is that you start with an initial data set, you'll eventually asymptote to something that's close to Kerr. So if I take the Kerr diagram, this is my scribe plus, this is the event horizon. The idea is that if I start with an initial data set of some kind, I'm eventually going to move and produce something that's close to Kerr. And this was already known to Penrose in the 70s, and of course it was much too hard a conjecture to actually prove, because you had to prove something like weak cosmic censorship, first of all, which would tell you that this region actually admits a foliation by slices, and that is to say it's globally hyperbolic. So that was the
you had to solve this. Then you had to solve the asymptotic approach to the Kerr geometry. So you had to show that in this region something does really look like Kerr. So in the asymptotics of the evolution, that was very, very hard. And before you even tried to prove that, you needed to know something like Kerr stability and rigidity. The stability is to say that if you perturb Kerr, you'll eventually asymptote to Kerr, perhaps with some different parameters, but you won't move away from the Kerr family. And rigidity is to say that if you're stationary in vacuum and so on, then you basically have to be Kerr. And so the standard picture of collapse was to say, well, if you start, you end up with something that's like Kerr. Now, Penrose knew this was basically impossibly difficult. And so what he did was very clever. He basically said, well, if this picture is true, then what should be true as a consequence of this heuristic? And moreover, might that be something that I can actually go about and prove? So he did something. I'm going to draw it slightly bigger because I want everyone to see it very clearly. So here we're at infinity. We've got a nice quantity which we know is the ADM mass out here, evaluated on spheres that we take out to infinity. This is my scri plus, and this is my time like infinity. Now, we know in the Kerr diagram, suppose this was the Kerr diagram, we know that in this region here, the evaluation of the Bondi mass is equal to the following, where what I'm doing here is I'm evaluating a quantity along some surfaces that go out to scri, and I'm considering A as the intersection of this slice, let's call it V, with the event horizon. So I'll just use the standard acronym. So A simply is defined as the intersection of V with the event horizon. Okay? So we know that this is true in Kerr. Good. Now, because of gravitational waves, LIGO, etc., that we can do, we know that when we evaluate the Bondi mass, which is an integral going out along these null hypersurfaces, we know that essentially as we're moving up into the future and we're evaluating the Bondi mass along the future, we've lost this energy out here. So the Bondi mass, as I go back down into the past, if I consider the Bondi mass, it should be going up or staying the same. And moreover, as it goes down, it should approach the ADM mass. And so this should be true, this inequality, where now this is the Bondi mass that I take along successively more into the past slices. And then Hawking, with some dubious differentiability assumptions on the horizon, on scri, and so on and so forth, proved the Aria Theorem, which would tell you that as you go down here now, the area should be going down or should be staying the same. It's non-decreasing towards the future, so non-increasing towards the past. And so notice now that I can just take any old slice. I know by this that there is a globally hyperbolic foliation, etc. So I can take any old slice, evaluate this quantity as I go down, evaluate this quantity as I go down, but the area here, which was the area at the top of the diagram as I asymptote to Kerr, should be going down as I go up here because it's the opposite of the Aria Theorem. So in other words, this should be true for any slice. So the beauty of this argument, now ignore this central piece and just consider this. This should now be true on any slice out here that intersects the event horizon. This is the Penrose Inequality, and it's been proven in special cases. So, in special cases, by Heuristic and Ilmanen in 01 and Bray in 01. Very, very beautiful, very, very difficult, beautiful geometric arguments, and totally different, which is kind of amazing. So you can ask the question, this inequality is a statement about the ADM mass, and the ADM mass, as we all know, is some limit of spheres as they go out to infinity, as r takes infinity, of some integral over a 2-sphere of some components of the metric. This is the ADM mass. And you can ask, is the Penrose inequality true, not for the ADM mass, but for some quasi-local measure of mass? And this is the first result that I'll present today, is that, in fact, it's now a theorem that the Wang-Yao mass of some bounded region satisfy a number of technical conditions is bounded below by the area as conjectured in the Penrose inequality. So recall that in the Penrose inequality, this area here was just the intersection of the event horizon with the slices. In our case, we're considering a slice, and we're considering, say, some minimal surface or event horizon or marginally outer trap surface, whichever detail you want to fix. But we prove now this inequality where this is the area of the outermost marginally outer trap surface, which would be an initial data stand-in for a quantity living in this intersection. So that's the first result. So, you know, hooray. The nice thing about this inequality is that it's the first time anyone's proved it in the space-time context. So previous results were all Riemannian. This is the first space-time result, namely where the scalar curvature doesn't need to be assumed to be non-negative and so on and so forth. But I'm not going to go into the details of the technical conditions. But that's the first point. And then the second point, and I knew I wasn't going to have really that much time, and so I'm just I'm going to state it, but then really I want this to be a discussion over cake perhaps, or in the question session. The Hoop Conjecture, which I rubbed out, was essentially a statement by Thorne which said that, let's suppose I have some region here, and I want to crank up the quasi-local mass associated with this region. So this is the boundary of some region, omega, and I want to prove that if, so this is the conjecture, so if the quasi-local mass is bigger, in what sense we don't know, than some geometrical quantity associated with the boundary, which one we don't know, which mass we don't know. So you see why it's not really a conjecture, right? So physicists, I mean, I see the Hoop Conjecture as Thorne's plea to geometers to have fun. And you know, it's a great plea, and we do have a lot of fun. So thank you. But anyway, you try to prove that if some region with quasi-local mass and is bigger in some sense to some boundary geometry quantity, then in fact there's a minimal surface or a marginally outer trap surface, which would be the kind of space-time generalization. And then the second result, which I wanted to show you and to present today, was in fact now this is a theorem. So that under the same kind of technical assumptions that go into this theorem, we prove that if a certain mass quantity, which we define, is bigger than a quarter of the diameter of the boundary of the geometry, then there is a black hole inside omega. By black hole, I mean a marginally outer trap surface. By diameter, I mean the sup of the distance between any 2 points P and Q for the induced metric on the boundary, where P and Q live on the boundary. And by M, I mean a really non-trivial, difficult quantity that it would take me more than an hour just to define and motivate. So I'm not going to tell you what M is. But I can just tell you it's a quasi-local mass. We also prove that if this is the case, if this is bigger than the Wang-Yao, so if this mass that we toyed with, if it's bigger than the Wang-Yao mass, then we also get the same conclusion that there exists a black hole. So that's all I wanted to say today. We have a new proof of we have a new statement, which is the first space-time localized Penrose inequality. It's first of its kind. And we have the first statement, first proof of the Hoop Conjecture in the sense of having a quasi-local mass and some boundary geometry. Thank you for listening.
All right, thank you, Martin. Questions?
So, from an astrophysics point of view, the way to think of it is if you assemble a certain amount of mass within a small enough volume, you must have a black hole. But you did not refer to a volume, you referred to a length. Why is that?
That's a very good question.
Or is it equivalent?
No, it's certainly not equivalent. So I could give you the honest short answer, which is that's all that we could do. In particular, some of the mass quantities, the way that you control the size is by some of the quasi-local mass ends up looking like some integrals over the mean curvature. It's more complicated than such a formula, but schematically this is the case. And then we use what's called the Minkowski Inequality once we isometrically embed into Rn to bound this quantity. And the way we do this is a well-known thing. You do it in terms of some quantities living on the boundary, such as the diameter. However, the honest answer to your question, so that was a short practical answer to your question. The honest answer to your question is, I've been thinking about trying to get different quantities such as volume, and so far no success, but it would be very nice to have something different here.
So are you saying that if I contract a mass in one dimension only to a slab, I will also get a black hole? I need to do it in all 3 dimensions, right?
Yeah, that's right. So the diameter will be the soup. So if I take if I have something like this, this length might be very small, but this length is going to be very big, and that's not going to do it here.
Any other questions? Okay, let's thank Martin and all the other speakers.